Welcome in everybody to our next N3AS seminar of this lovely fall semester. And today we're very pleased to be joined by Will Newton from Texas A&M Commerce. And Will is going to tell us about what we can infer about neutron stars from multi-messenger nuclear astrophysics. So please, Will, whenever you're ready, take it away.
Thank you very much. It's great to give this seminar to this collaboration. I'm going to talk about multi-messenger constraints on neutron stars, and I'm particularly interested in the crust of neutron stars. And we'll explore why that is as the talk goes on. The work that I'm going to show you would not be possible without the undergrad and master students that I have, who are amazing. They're shown in red here. And so much of what you'll see is their research. At the bottom here is a little pie slice through a neutron star and a zoom in of the crust that was adapted from a figure by my 13-year-old niece, and I like this much better, so I'm keeping it. Okay, so in the last decade or so, we've seen a coming together of a vast array of experimental, observational, and computational data to measure strong, weak electromagnetic and gravitational signals. The number of experiments we have probing observables is getting large enough that it's a struggle to represent them on a slide. But we have X-ray telescopes, we have the NICER telescopes on the International Space Station, we have the LIGO-Virgo gravitational wave telescopes, we have radio telescopes, we have a whole host of nuclear experimental facilities, including one that is that's caught a lot of interest recently, in the form of the P-REX experiment to measure the neutron skin of lead. And all of these facilities are in service to probing a wide variety of physical phenomena that are all linked together by the fact that their behavior is driven at its core by nuclear physics, by a model of nuclear interactions. And there are a number of aims for bringing all of this data together. And the first one is we want to understand neutron stars better. Why are they the way they are? You know, we know that we have some solid evidence that they have a solid crust and a liquid interior, but there are large uncertainties about the structure and composition that we would like to pin down. So I've illustrated the neutron star here with the outer three layers are the outer crust, the inner crust, and then there is a possible layer of exotic nuclei called the nuclear pasta phases, which I'll mention a bit more of later on. And then we have a core, which is expected to be neutrons, protons, electrons, muons, before at some point we suspect that, or the validity of a nuclear description of matter almost certainly breaks down, and we need to consider possibilities like a deconfined quark phase. So we're also interested in the nuclear physics of all of this, of trying to map out the phase diagram of strongly interacting systems. So this is a depiction of the phase diagram. There are three axes: temperature, density, and isospin asymmetry. And neutron stars occupy much of the lower temperature plane of this diagram, reaching up to higher temperatures at birth and at death. So they're born in the fire of a supernova explosion, and they die in the explosion resulting from a binary neutron star merger. So we want to map this out, and in doing so, understand the properties of nuclei better. And then finally, and I think this is particularly important, but goes unsaid more often than our other aims, is neutron stars exhibit a whole host of behavior. They lead very rich lives. They are born, they cool, they slow down, they glitch, they may spin up again, they may heat up again. There may be epochs of heating followed by cooling. They oscillate, they merge with binary companions. There's a whole host of neutron star behavior that we would like to understand from a purely astrophysical point of view. We want to, for example, connect together the periods of a neutron star's life. And to do that, we need a solid understanding of the structure and the dynamics of neutron stars. So you can list a lot of observables, right, on the nuclear side and on the neutron star side, all of which, hidden within all of them is some information about the properties of dense matter. Sometimes that information is more accessible than at other times. And we want to ask ourselves, how do we pull this data together? How do we harness it all in a way that makes sense, in a way that has well-characterized model uncertainties, and to understand dense matter better? So the modern approach is to create ensembles of equations of state and neutron star models that you can use in various statistical inference schemes. For example, you can use them as some prior distribution, some prior ensemble in a Bayesian analysis, and infer posteriors over for example, the neutron star equations of state. And so this has been done quite successfully over the last decade. And has become the standard way to analyze especially data from X-ray telescopes measuring the radius of neutron stars, radio telescopes measuring their masses, and gravitational wave observatories measuring their tidal deformability. And from this, we can begin to glean some of the physics of the interior of a neutron star. Right? We have a basic picture of a neutron and proton fluid. We're seeing tantalizing hints of a possible phase transition to quarks from this analysis. The one sort of interesting example is on the top right here. There's this plot of the speed of sound within the core of a neutron star versus density. And several studies have found that the posterior distributions contain a softening of the equation of state just above nuclear saturation density. So work on all of this is ongoing. We're going to have increasing quality and quantity of data coming in. But I want to draw your attention to the neutron star crust, which at the moment, for the most part, is left out of these studies. But it's very important. So we know that the crust of a neutron star is solid, and we also know there are superfluid neutron stars in the inner layer of the crust. We know this by watching neutron stars in low mass X-ray binaries cool over time. And we can plot, for example, their temperature versus time since the end of an accretion phase. And in order to fit these cooling curves, you have to have a crystalline crust with superfluid neutrons. So we have very strong evidence of the basic properties of the crust. But we can go much further than this. Studies of the crust have, for the most part, still use the more, or the older method of just examining the properties in question using a limited number of equations of state. But what we want to do is calculate ensembles of crust models that are consistent with the core equation of state. So, which would result in a plot that looks like this. So this is just pressure density again. This is your equation of state plot, but now the x-axis is logarithmic, and that emphasizes the crust more than the, for example, the plot above it, where the crust is squished into the bottom left of the plot. So what we would like to do is use these ensembles and to start to bring in data that probes crust properties, and start folding that into our statistical inference of neutron star properties and the equation of state. There are a lot of observables that are sensitive to the crust, which I've highlighted here. So I won't run through them all. The point is, there's a lot of data we already have on phenomena that are crust related, and we want to make use of them. So that's the bottom line here. So I'm going to first take you through the way we construct our consistent models of crust and core equations of state. And I'm then going to run through an example of a potential observable and a statistical inference from a piece of pseudo data for that observable, and demonstrate how it can constrain both the crust physics and the core properties of a neutron star. So this is a sort of little flow chart that I put together to try and come up with a nice visual for the flow of model to calculation of observable to incorporation of data, Bayesian inference, and back to where we started. So from my point of view, at the very heart of all this is a nuclear model. And that nuclear model should be used to calculate the crust equation of state and the core equation of state. At some point, we have to move on to some other description of the high density equation of state, because we know nuclear physics has to break down somewhere. But armed with this full model of a neutron star, we can calculate astrophysical observables like masses, radii, tidal deformability, and crust properties. And armed with these distributions of observables, we can, essentially these distributions enter as priors, and then we feed in astrophysical data into our Bayesian analysis, and out the other side we get our posterior distributions over the model parameters. And at the same time, we can go the other way. We can use our nuclear model to calculate nuclear observables, like binding energies, like neutron skin thicknesses, and then feed that into a Bayesian analysis with nuclear data and obtain the posteriors from the nuclear experimental side of things. And both of these feed back into the nuclear model and allow us to refine the nuclear model. And over time, with more data, we can hone in on the nature's true model of the nuclear interactions and the state of matter in a neutron star. So we need to choose a nuclear model, and we need to parameterize that nuclear model in some way. And the way we have chosen to parameterize it is in terms of a set of parameters that define a quantity called the symmetry energy. Now, the symmetry energy is shown in this plot here. The blue line is the energy per particle of symmetric nuclear matter, and the red line is the energy per particle of pure neutron matter. And the symmetry energy is essentially the difference between these two extremes of nuclear matter. And we usually deal with parameters that characterize the symmetry energy around nuclear saturation density. So I'm going to use J to refer to the magnitude of the symmetry energy at saturation density. I'm going to use L to for the slope of the symmetry energy proportional to the pressure of pure neutron matter, and K-sim, which is the curvature of the symmetry energy at saturation density. And these are going to be my three independent parameters that I'm going to use in our nuclear model. More parameters can be included, and it is important to assess how many parameters do we need to capture all of the necessary physics, and how many of these higher order parameters in this Taylor expansion can we safely ignore. One point I think is important to make is that different nuclear observables and astrophysical observables constrain nuclear matter at different densities. So on the left here, we have a plot of a number of constraints on the symmetry energy as a function of density from a number of different experiments measuring different observables, and the constraints that come out constrain the symmetry energy at a number of different densities. Now, we should therefore be a little wary when we look at, for example, very nice summary plots of the constraints on, say, the symmetry energy and its slope at saturation density, or the slope and the curvature at saturation density, because in most cases, to obtain those constraints, you're having to choose a model to extrapolate from the density at which the observables sit to saturation density. And there are many different forms of the nuclear symmetry energy that you could potentially use. And so these various constraints do not all use the same functional form for the symmetry energy. So this is one reason why it is important to choose one model and try and calculate as much as you possibly can with it. So we choose the Sturm-Hartree-Fock model. It is given here as an energy density functional. There's a whole bunch of terms corresponding to different aspects of the nuclear force. But the basic thing you need to know is it is a function of density and isospin asymmetry. And there are a bunch of parameters, a bunch of model parameters in here. But those model parameters can be mapped onto nuclear matter parameters, which have some more concrete physical meaning. And they include the symmetry energy parameters. So given a set of nuclear matter parameters, we can construct a Sturm model. And this is nice because we're going to, we have a much better chance of coming up with sensible priors on the nuclear matter parameters. You know, the priors on the Sturm model parameters, we don't know. We don't know what they are. So in practice, what we do is we fix the nuclear matter parameters for symmetric matter at saturation density. And that gives us a sum of the Sturm parameters. We use chiral EFT calculations of pure neutron matter to get a couple of other parameters. And then we choose our 3 free parameters to be these parameters x0, x3, and x4, which are mapped from JL and KSIM. So the general strategy is we start from a prior distribution over the symmetry energy parameters from which we can calculate our ensemble of nuclear models. We also need a model for the crust. There are various ways you can go about calculating the crust, from the fully microscopic, which is shown in a sort of cartoon form on the left, where we treat neutrons and protons fully quantum mechanically, and we solve in 3 dimensions the system of coupled Schrödinger equations that come out of the Sturm-Hartree-Fock method. And this has the advantage of consistently including quantum effects. You can do it in 3 dimensions, and you can consistently include all parts of the nuclear interaction, including gradient terms, which allow the surface energy of nuclei to emerge consistently. And we've performed lots of these calculations, especially focusing on the nuclear pasta phase at the bottom of the crust. There's a couple of pictures from our calculations up here of a spaghetti and a lasagna layer. But these models are very computationally intensive. And so if we're going to calculate on large ensembles of crust models, we need to choose something simpler and more computationally expedient. So we choose the compressible liquid drop model, kind of the opposite end of the spectrum, where our degrees of freedom are just the properties of the neutron fluid inside and outside of the nucleus, and the surface or the interface that divides them. And so in this model, the Sturm energy density functional can still be used to calculate the neutron matter outside the nucleus and the neutron and proton fluid inside the nucleus, but a separate function for the surface energy has to be specified, which brings in a number of extra model parameters. I'm not going to talk about the surface parameters much in this talk. We typically fix them in a couple of ways, often by fitting this compressible liquid drop model to nuclear data. But there are, you can discuss a lot of issues surrounding that. And that's not going to be the focus today. So we're going to take this model to construct our neutron star crusts. So to summarize, our model is characterized by the 3 symmetry energy parameters, JL and KSIM, throughout the entire inner crust and up through the core, up to a density of about 1.5 times saturation density. We then append 2 polystropes above that density to account for our ignorance at higher density. This is a very simple extension of the equation of state. There are many more sophisticated ways of extending the equation of state to high density that have been explored in the literature. But for our purposes, we really want to focus on getting a consistent nuclear model down here up and running. So 2 polytropes for the moment is enough for our purposes. So we now have our nuclear model. And oh, there's a hand raised.
Yeah, thank you, Will. This is great. This is George Fuller at UCSD. So what are the indices that you typically use for the 2 polytropes?
They are so the 2 indices, the things I listed there, N1 and N2, are the polytropic indices.
Yeah,
so,
what are they? What do you
they are, so it's when you write the polytrope, it's rho to the 1 plus 1 over n.
No, I understand. So, but what are the indices that fit best?
Oh, the ones that fit best. I apologize. So I will show you plots coming up of the posterior distributions of those.
Okay, thank you.
Okay. Okay, so we can now get to work. We can use, we're going to use a bunch of astrophysical and nuclear data. The main data we use is highlighted here. So the NICER telescope has measured 2 objects, the radii and masses of 2 objects, which are shown in this figure on the left here. This figure on the left is actually taken from a recent paper which claims to have also measured a low mass neutron star, which may or may not go away, but it would be really, really nice if it sticks around. There is the LIGO-Virgo measurement of the tidal deformability of a neutron star. And then there is a host of data on the neutron skins of neutron-rich nuclei. The P-Rex experiment and the C-Rex experiment have understandably got all the press in recent years. But I do like to remind people that there is an awful lot of data that has been collected prior to that. And that data itself is, contends with a whole host of uncertainties and model dependencies. But I think that for the purposes of this talk, I'm going to include all of that data when we come to use neutron skins to constrain our models. Okay, so with that said, what do we get out? What do our posteriors look like? So firstly, I'm going to show you the posteriors for the purely crustal quantities. So these are posteriors over our crust models, not the full neutron star models. And shown here are the posterior distributions oriented vertically. The blue and orange refer to two different choices of surface energy parameters. Again, I won't go into that in detail here. And then the 6 distributions correspond to the prior and combinations of the P-Rex neutron skin measurement alone, all of the neutron skins measurements for calcium-48, lead-208, and the tin isotopes. And then the same again, but with the inclusion of constraints on pure neutron matter from chiral EFT. So you can see that we get progressively stronger constraints as we add these observables. But the medians are all, do not change a huge amount as one goes across adding data. And in fact, the posterior that includes the most data predicts a thickness of the nuclear pasta layers relative to the crust of about 12% of the crust, and the mass of the pasta layers compared to the mass of the crust is around 50% for the median values, and the uncertainties are given here as well as about 20% above that, 40% below that. And this is illustrated schematically by these bars below, just to give a visual on the median predictions for the amount of nuclear pasta in the star. So the message here is that one should take the properties of nuclear pasta, or the existence of nuclear pasta, seriously when developing models models for phenomena that may involve the inner crust or the crust core boundary. These figures are actually in line with predictions from similar studies, although there are 1 or 2 studies that come to quite different conclusions, although those studies tend not to have been studies using whole ensembles of crust equations of state. But there's still some wiggle room, right? We cannot rule out the possibility that there is no nuclear pasta. Okay, so moving on to our full neutron star models. Here I have plotted the parameters J, L, and K sim versus the radius of a 1.4 solar mass neutron star and the neutron skin thickness of lead. And there are 4 different posteriors, or 1 prior and 3 different posteriors shown here. 1 posterior for the NICER LIGO data, 1 for the neutron skin data, and 1 for the combination of the both. The basic message here is that the NICER LIGO data tends to prefer a stiffer L and K sim, whereas neutron skins prefer softer L and K sim. Now note that P-Rex alone would come to the exact opposite conclusion. Its measurement is of a very stiff neutron skin. So this is simply the conclusion when one takes into account all of the neutron skin data. But what it does demonstrate is that the neutron skins and NICER and LIGO are having some influence on the predicted values of the symmetry energy parameters. we can now take a look at the thickness of the crust relative to the star, the mass of the crust relative to the mass of the star, and so on. The mass of the crust is given in what some might call slightly funny units. It is actually measured in terms of a time scale for a crust to be completely replaced by accreted material if the accretion is happening at the Eddington accretion rate. So this typically gives a range of around 1 to 10 million years. And here, main thing to note here is that the ASTRO data prefers a thinner, less massive crust, and neutron skin data and NICE LIGO data both still proven informative for crust properties. So both ASTRO and nuclear data are having an influence on the predicted properties of the crust. This is the same plot except for the nuclear pasta regions, and we come to the same conclusion here. ASTRO prefers thinner pasta region, neutron skin data, and NICE LIGO are both informative. Okay, if I can take 5 minutes, I want to run through a concrete example of using this with a potential astrophysical observable to obtain constraints on the nuclear symmetry energy and crust and core properties. So this is work that I did with Duncan Neal and David Sang of the University of Bath in the UK. And what we were looking at is the potential phenomenon of resonant crust shattering flares. So the basic idea is illustrated in this excellent cartoon picture. So we have two neutron stars in spiraling, and when they get close to merging, their tidal forces that they're exerting on each other excite crustal resonance modes to resonance. And that resonance can shatter the crust. So the breaking strain of the crust can be exceeded. There is a cracking of the crust. There is a scattering of the energy down to smaller and smaller length scales, so the crust eventually completely shatters, and then magnetic coupling to the magnetosphere creates a gamma ray flare. Okay, so this is one possible astrophysical scenario, but what we can do is look for evidence of gamma ray flares very shortly before a neutron star merger. And we have seen some of these. These are a couple of examples of flares, of gamma ray flares that were detected somewhere in the region of 0.1 to 10 seconds before the soft gamma ray burst, which we presume to be the neutron star merger. So sometimes something appears to be going on, and resonant shattering flares are one possible explanation. The really nice thing is if we can coincidentally detect the gravitational wave signal from the in-spiral and the gamma ray flare, we find that this can actually measure the resonant frequency of the crust. Okay, because the measurement of the flare gives the time before merger that this shattering occurs. And so we can go to our gravitational wave signal and just read off the frequency of the signal at that time. And that frequency is going to be twice the resonant frequency of the crust. So this is a potential way of measuring that frequency. And with our models, we can calculate all the relevant quantities needed to, or needed as input into models of these resonant shattering flares, including the shear modulus around the base of the crust. And the shear modulus can be used to calculate the shear speed, and we find that there is a very strong correlation between the average shear speed in the crust and the I mode frequency. The I mode is the particular mode that becomes unstable. It's the interface mode between the base of the crust and the core. So what we did is we injected a synthetic detection of a resonant shattering frequency, a resonant shattering flare at a frequency of 250 hertz. And we use that as data in addition to NICE LIGO data and data on nuclear binding energies. And we inferred posterior distributions on our 5 model parameters. So the 5 parameters are shown here. The top left panel is the magnitude of the symmetry energy. As you go along left to right in the plot, what you are seeing is the prior distribution plus NICE LIGO, the prior plus the resonant shattering flare frequency, the prior plus both of those astrophysical observables, then the nuclear data, and then the nuclear plus all the astrophysical observables. So you can see here that the magnitude of the symmetry energy really isn't particularly sensitive to the astrophysical data. And it's only when the nuclear data comes in that there is a strong constraint on the symmetry energy. And interestingly, when one combines both the astro and the nuclear data, one gets an even tighter constraint on the symmetry energy. For L and K sim, it's kind of a mixed bag. The astrophysical observables constrain L and K sim somewhat, and the nuclear observables constrain them somewhat as well. So both nuclear and astro data are giving us information on L and on K sim. Then at the bottom are our 2 polytropic parameters, N1 and N2. I'm plotting the log of N1 and N2 here. And we start off with uniform priors on the polytrope parameters. And unsurprisingly, the astrophysical data that probes the core, namely the NICE LIGO data, strongly constrains the polytropic parameters, but the astrophysical observable sensitive to the crust does not, nor does the nuclear data. Okay, so, and one can add these constraints to these famous plots showing a whole host of constraints on the magnitude and slope of the symmetry energy. And the takeaway is that this is for a single injected frequency. And these are giving constraints that are competitive with some of the nuclear constraints that we are getting. So the blue are the posteriors for from our resonant shattering flares. These left and middle are for 2 different frequencies that we injected. And then on the right, this is the shattering flare frequencies combined with the nuclear binding energy data. So, okay, so takeaways from all of this. So we have a model that efficiently calculates crust and core properties. Both nuclear and astrophysical data give us information about the neutron star crust. So it is important to calculate ensembles of crust models that are consistent with the core models that we use to take advantage of the crust observables. And then I gave a specific example of the resonant shattering flare. I showed how a coincident detection of a flare and gravitational wave signal can measure the I mode frequency and constrain the nuclear symmetry energy. And there are a number of caveats that I haven't had time to list here. There are model dependencies still at all steps of this process that we just must work to improve step by step. For our particular scenario, one can, of course, ask the question, how do you know that the flare that you're looking at is a resonant shattering flare and not something else? One could turn that around and say, if we accurately measure the symmetry energy, then that would predict the resonant frequency of the crust and therefore allow us to test whether these flares are resonant shattering flares. Okay, I'll leave it there. Thank you for your attention.
Thank you, Will. Do we have any questions? Please raise your virtual hand. It looks like we have a question from Yang Bai. Please go ahead.
Thank you for the interesting talk. I just have one more question about the crust. You mentioned the one signature for crust. I'm wondering, after merger, after neutron star merging, any other information about the crust we can observe, which could be used to distinguish different models of the neutron star?
Thanks. So it is unlikely that we will be able to extract information about the crust post-merger, simply because the crust is, during the merger, the temperatures are high enough to completely melt the crust, and the outer parts of the star quickly get processed, and so the crust is basically destroyed in the merger. So we're unlikely to get information that way.
Thank you.
Sherwood, the floor is yours.
Thanks. Thanks for the great talk. So if I understand correctly, you have this global model of the entire neutron star, but part of it's this polytrope that I think you mentioned is just parameterizing ignorance. Is there a possibility that that some high density format that doesn't match that functional form could pollute the crust inference you make? So for instance, if it was like a phase transition.
Yes, it definitely could. Yeah. So if there is, for example, some sudden softening of the equation of state at high density, then the crust depends not just on the crust equation of state, but the whole of the star. The larger the star, generally, the larger the crust. So yes, the fact that we don't include large phase transitions in our model means we are not spanning the full space of equations of state, and that may have that probably will impact our inferences on crust properties.
Okay, thanks.
Go ahead, Tianqi. I don't think we can hear you, Tianqi. Perhaps I think you had an audio problem last week. Maybe you can check into that while we hear from Atul.
Yes, hi. Great talk, Will. My question is about the EOS at really high density at the perturbative QCD limit. Do you constrain your EOS up there or leave it free for the piecewise polydropes to take whatever form they want?
Yeah, we leave it free, so we don't have those those very high density PQCD constraints on. We allow our we switch. So if our polytropes if our polytropic equations of state exceed the speed of light, then we switch to a completely causal equation of state. But yeah, we don't do anything else up there.
I see. So there's at least some constraint on it not being acausal.
Yes, there
yeah,
is.
yeah. Okay. Great. Thank you.
Okay, I think my mic
Yes,
is
we can hear you now.
Okay, thank you, Will, for the nice talk. I have a question about your last plot here. You add binding energy constraint in the last plot here. How
Yes.
about the previous plots that you did with all the equation of state and the saturation properties?
I'm
The
sorry, could you
binding
repeat
energy
that
constraint
last
is not
sentence?
imposed, right?
Sorry, could you repeat that last sentence?
So the binding energy constraint is not imposed for the previous plots. So do you impose binding energy constraint for those?
They are
saturation?
for these plots, the binding energy constraint is imposed in the one on the right.
Yeah. So how about those crust? Your conclusion about the crust? Did you put the binding energy constraint on those?
Oh, I'm sorry. We have done, though I don't have those plots on this talk. So you mean
the ratio, the radius ratio and things like that?
yes, things like this. Yeah, for including the binding energy data. Yeah, so we have done that. They are just not presented here.
Does it change the result, or it's still something similar?
It changes it somewhat, yes.
Okay, got that.
It's the binding energies really constrain J.
Okay.
And so that does constrain certain cross properties.
Okay, I have another question about this I mode oscillation. Does it depends more on the nuclear equation of state, or it depends more on the crustal structure of the neutron star crust? I mean,
It so it depends on so in our model, it basically depends on the shear modulus at the crust core transition, and therefore the density and pressure at the crust core transition.
yeah.
So the shear modulus depends on the composition.
Yeah, and also temperature, right?
Yes, but we are in a regime where it's still cold enough that temperature effects are going to be negligible.
Oh, okay. Yeah. Thank you.
Yeah, so it does both composition and the pressure density at the base of the crust affect the IMO frequency.
Okay, that's very interesting. We can really see such a signal from the merger. Thank you.
Yes.
Last call for questions. I don't see any hands, so let's thank Will again. And we hope to see everyone again in 2 weeks for our next N3AS seminar.